Hi, this video is about hash functions. These are the mathematical functions built into hash tables that are responsible for mapping keys into indices. So this video covers how we can create such things. So the goal is to implement the map abstract data type. We want to be able to find based on keys, insert pairs with keys and values, erase based on keys. So the key type will be some abstract data type, but often in practice is an integer or string, but maybe it could be a different data type. And what we need to do in order to make the data structure work is define a function called hash of key. So hash is a function that takes a key object as input and returns a unsigned integer that's suitable as an index into a big vector. So that we can have an invariant kind of like this. V at index hash of key is a pointer to the pair that has that key, or null to say that there is no such thing. Well, here's how we would like these functions to work in our dreams. So if we could, here's what we would like to have. That number one, the hash function, any hash function is consistent. So that means if x and y are two key objects that are equal to each other, then the hash of x is equal to the hash of y. We need this property so that if we insert something into the hash table, we can find it again later. So it needs to be the case that if I want to deal with this key 4 value dog pair over here, that the first time I insert that pair into the table, I'll hash 4. 4 is a key, so hash 4. And if that hash function says index 1, and we store the pair at index 1, then later on down the road, if I want to find that pair and I call hash on 4 again, I need to get 1. If sometimes this hash function gives us 1 and sometimes it gives us a different value, if it's kind of flaky like that, then we won't have a usable, reliable hash table. So we need consistency. And then what we would have in our dreams is that there are no collisions. So no two keys ever map to the same index. We would like that to be the case. So that would mean, the way we could say that is if x is not equal to y, so I have two different keys, then certainly hash of x is not equal to hash of y. We'd like that to be the case. Here's some bad news though. Property 2 is actually impossible. It's mathematically impossible to have a hash function that gives us this guarantee. So that means collisions are a possibility. It's possible that we'll have multiple keys mapping into the same index, and that's just something we have to deal with. Let's see why that is. So hash of key, again, is a function that's given a key data object, probably an int string, and it needs to return an integer that's a legal index for an m element vector. Namely, it needs to be an integer in the range 0 through m minus 1. M is going to be chosen as a reasonable size for a vector of n elements. So for example, we might define our data structure to keep m always less than or equal to 2 times n. So here n is the number of pairs in the hash table. In my example on the previous slide, I had n equals 2. I had 2 pairs in that table. So maybe m is never more than twice n. So if I want to have, I don't know, a 7 element hash table, if n is 7, 2 times 7 is 14, maybe m would be the next bigger power of 2, like 16 or something like that. But the point is that we want to have a reasonably compact table. We talked about in the previous video about how we don't want these billion element hash tables for small data structures. Well, the problem with that is that the number of possible key values is much larger than m. This triple greater than symbol means much, much greater than. As a consequence, multiple keys then have to map to the same index in the range 0 through m minus 1. This is an example of the pigeonhole principle from mathematics. If you've had the opportunity to take discrete mathematics or proof techniques, you've probably learned about the pigeonhole principle. In the abstract, the pigeonhole principle says that if I have n pigeons and they fly into n minus 1 pigeonholes, so there's one more pigeon than there are pigeonholes where pigeons sleep, then somewhere there's got to be one pigeonhole with two pigeons in it, right? There has to be at least one doubling up. That's the only way that can happen. We have a similar situation here where I have something like billions of different possible key values and something like dozens of different indices. And so if every key maps into a index, there's got to be some doubling up that multiple keys map to the same index. It's just the only way this can happen. here's how we could illustrate this visually. So I've illustrated these two sets as kind of mathematical sets as ovals here. So on the left side, we have the set of all possible key values. On the right side, we have the set of all possible index values. Our hash function maps a key value to an index. So we could envision that if we pick an arbitrary key, like 1 and 4 were the keys in my example, if you call hash on key, it maps that to an index in the range 0 through m minus 1. So practical values here might be that if we use a 32-bit int as a key, 32-bit ints have about 4 billion possible values. So this set here has approximately 4 billion different keys that could exist. And then if I have a vector of 16 elements, then m is 16. So I have 16 different indices, 0 through 15. So there's no way that every possible key could map to a different index because I have billions on the left and 16 on the right. If I tried to set this up, let's say, okay, the first key maps to index 0, the second key maps to index 1. I could get through the first 16 keys, giving every key a unique index, but once I get to the 17th key, I have to pick an index that's already been picked once. So we have a situation like this at the bottom here where there are certainly multiple keys that map to the same index. We call that a collision. And that's something our data structure is going to have to deal with, that multiple pairs might get mapped into the same index. So we have to deal with the existence of collisions. There's no getting around that. But what we can do is kind of try to reach a compromise. And the compromise we reach is that we settle for improbable collisions. We don't say they never happen because they have to be a possibility. But instead we say that the collisions are very unlikely. And we have a definition for a kind of a hash function that gives us that guarantee. It's called a universal hash family. In mathematics, a family of functions is a collection of functions that are basically the same, but they vary a little bit. There's like parameters that make them slightly different from function to function, but they all work basically the same way. So a universal hash family is a family of hash functions that make collisions very unlikely. And so if we can define one of these in our computer code, then we can pick a random function out of a family of similar functions and use that for a hash table, and that will make collisions unlikely, still technically possible, but unlikely to happen very much. So that's how our hash table data structure will work. When we create a hash table in its constructor, we will pick a random hash function out of a defined universal hash family, and then that data structure object will use that hash function for its lifetime. That means that the number of collisions that hash table experiences becomes a random variable. There's a random element to this since the data structure doesn't know what keys will be inserted when it's created. It just picks a random hash function, and we might get lucky and have a hash function that makes for very few collisions, and we might get unlucky and get a random hash function that makes for more collisions. There's a random element to that. That will cause the runtime of some hash table operations to be a randomized variable, and the runtime of some hash table operations is constant expected time. Expected means on average in this randomized scenario. We'll get into what that means in the next video. Here's the definition of what a universal hash family is. So if hash of key is a hash function chosen randomly from a universal hash family, then two properties are given. One is the consistency property, that if x and y are two equal keys, then hash of x is equal to hash of y. So that's so that we can insert a key into a table and then find it again later. And now we have rare collisions. It doesn't say no collisions, it just says rare collisions. So that says if x and y are different, x and y are two different keys, then the probability of the event that hash of x is equal to hash of y is very low. The probability is less than or equal to 1 over m. M is the number of indices in the table. So if we had that 16 element table, then the probability of two keys colliding is about 1 over 16, 1 out of 16, a very low probability. Okay, so the actual hash functions are usually defined to work in two steps. Remember that the key type k could be just about anything. It could be just about any data structure you want. It could be int, float, char, string, a user-defined class, whatever. So to deal with that in practice, usually the hash function is a two-step process. There are two separate functions that implement hash of key. There's a first function that I'll call code of key, and what the code function does is it maps the key type k into an unsigned integer. So If k, the key type, is unsigned integer, then that code function doesn't have anything to do. But if the key type is a different data type that's very much not an integer, like a string, then code needs to do the work of turning that string into an integer somehow. Then there's a separate function that we'll call h to be consistent with our primary sources. And what h does is it takes an unsigned integer called a code, and it maps that code into an array index. So code function, the code's job is to take this key data type, which is not necessarily even an integer, and get it to be an integer. And then h's job is to take this humongous integer, there's no bound on how big the integer is, and map it into a valid index in the range 0 through m minus 1, and also provide that universal rare collision property. This makes this hash function design modular. This is to achieve modularity. So the universal hash family part h that deals with making the probability of collision low and making the range 0 through m minus 1, that h function doesn't have to know about this other aspect of mapping the key type into a integer data type. Here's some examples of how the hash code key could work. So code is a function that's given a key of type k, and it needs to convert that key object into an unsigned integer that we'll call a hash code. So if the key type is an unsigned to begin with, we just return the key unchanged. That's a trivial code function. If the key type is a signed integer, a positive or negative integer, we need to take that positive or negative integer and map it into a non-negative integer. One way of doing that is just taking the absolute value. So given an integer that could be positive or negative, take the absolute value, and we're left with a certainly non-negative integer. For a double is a floating point type. It's definitely not an integer. It could have a fractional part. There's a few ways of doing this. One way we can do this is just look at the bits in the double and treat it as if it was an integer, even though it's really not. So if we take the address of the key, that gives us a pointer to a double. If I cast that into a pointer to an unsigned, then I'm looking at the bits of the double floating point number, telling the computer to pretend they're an unsigned integer even though they're not, and then dereference it. That gives me that value. So it's a little bit ugly. I'm using pointers here, but it does work. Compound data types are more complicated. Compound data types are data types that have multiple elements in them, like string, vector, pair, or a container class that has a few data members. In order for the hash to work well, it needs to combine all of the elements in the collection. So if we hash a string, we need to involve every character in the string. Also, we want every hash code to be approximately equally likely. So that means that some simple ways of aggregating a compound data type don't actually work very well. For example, a string, it's tempting to just add up all the ASCII character values in the string, sum them all up, and return that as a code, but it doesn't work very well because of the way summation works and the way the ASCII code works. Certain keys become more likely. So this is a bit of a more complicated topic. I don't want to make this video too long, so I'll just refer you to the Open Data Structures textbook section 5.3. That talks about how you can develop codes for compound data types.